video, we're going to design a composite model for a company that we call B. I guess the best way to find the composite data set is if you go to, well, let's go to multiple variable multiple. Let's look at the branches, and we've got LOBs, and can you see it's B all, which comprises, well, let's find out what it comprises by just opening it. So why don't we open it? And if you go to the triangle groups, it comprises all these triangle groups. The data is actually a simulated composite data set from a company that appears on Schedule P. So what we did, we actually designed a model for a particular company for all these lines of business. We then, after designing a composite model, we just simulated a composite data set. So, I mean, I guess the data can be regarded as really in the sense that it reflects features and real data, but the actual sample values in the triangles are not the same as in the original real data. So the way we design a composite model, the starting point always is the models you've already designed in PTF with the corresponding forecast scenarios. So let's go to the composite data sets called CDS. If you click on composite data sets, these are all the pay triangles. Go back to the models tab, and let's go to related models. And what you do is you grab all the good ones. They're not all the same models. They're just named the same so that in the list, they're very easy to find. In fact, in this particular example, they're the only ones in the list. So I highlight them all with the right button of your mouse, select open, and it's going to go some iterations, and then it's going to complain that it needs to do more. Just say yes. You've got to stop it at some point anyway. Actually, it seems like it required less than 60 iterations. Okay, and the first thing we do is we're going to create clusters. So we go to the OC button, optimization of residual correlations. So let's click on that. And we're going to, well, we've calculated lots of correlations. I mean, what you could do if you wanted to, you know, where the correlations are insignificant, just to test them, you can always create a composite data set of just those two data sets and then run that in MPTF and check for correlations. But what we generally advise is if you've got many LOBs, you remove all insignificant correlations and then you estimate. And then just check to see that all correlations remain insignificant, and they do. And you can see most of the correlations are they're about 10 clusters. There are in fact 10 clusters, and most of them have very low process correlation. What's the highest process correlation? The 0.44 between special liabilities and other liability occurrence. I mean, you could in fact create a composite data set of just these two, and then perhaps study the residuals and see if you can see that correlation in the residuals. So now we just, well, I guess if we estimate again, nothing happens. You cancel, you save that as your good model. Let's just call it good. Well, obviously, I've done this before. Somebody has. Save it. Yes. Now I'd like you to load the model good again in a new window. Load model with the downward arrow, load model in new window, select good. Now tile vertically, minimize other types. And let's compare, for instance, on the left I'll compare PPA, private passenger automobile. On the right I'll have commercial auto liability. And you can see they have very different trend structure, which means that future trends along the calendar years are not going to move together as we did in the previous study where we looked at net of reinsurance versus gross. Net of reinsurance had common drivers, especially along the calendar years. if the trend along the calendar years in one piece would change in the future, then it would in the other piece, in the other segment. Whereas for these two lines, if there was a change in trend in the private passenger automobile, well, it's never happened in the past, so why should it happen in the future that you'll have a change in trend in the commercial auto liability? Even the process volatility is different. Process variance is different. You can compare, for instance, where do we have high correlations? So if we go back to OC, the two that had the highest correlation, process correlation, was SL and OLOCC. Other liabilities occurrence. Well, let's look at these two pieces. So on the left side, let's look at SL, and on the right side, don't worry that this is not significant. We won't worry about that because this is not what this exercise is about. OLOC, well, they have nothing that is similar. The development pattern is different, so on. Let's now remove run 2. So run 2 of NPTF, you just click on the X. And when you go to forecast, what you typically do is you load the scenarios. Well, these are already existing because I've done this before. You go to related and load the scenarios that you've had in PTF. Now, it's not often that you only have one scenario in PTF. You might have a conservative scenario, a reasonable scenario, and perhaps an optimistic one. But let's assume, in this particular exercise, for each line of business, we only actually saved one forecast scenario going forward. So you load these, and then you can save them as a composite save, and let's call it, well, actually, let's cancel that. I'd like you to go to periods and click on last future accident period. That's also forecast the next underwriting year or accident year, and also create a combined forecast table. Now let's save that forecast scenario as a composite forecast scenario called good combined. By combined, I mean we've combined, we've got a forecast table which is combined reserve plus future underwriting year, apart from getting the reserve table and the future underwriting year or accident year tables. So now just click on OK. Okay. Now, if you go to the extreme right of the table, we've actually forecasted to 15 development years. Now, typically, each scenario for each line of business, going forward, you might not forecast till 15, but the system takes the largest development period to be forecast to for any individual line of business and uses that when it calculates now the forecast for the aggregate in each line. Now, if for some lines of business you believe that after, say, development year 10, it goes to 0, well, you can always set your gamma parameter beyond 9 to be a strong decay like -3 for that line, and you'll get zeros for that line. Okay, we're looking at the aggregate table, and let's scroll to the bottom. And this is quite interesting. We've only forecast the development year 15, and let's suppose we suppose it runs up by 15, which is probably unlikely for workers' comp, but let's suppose it does. Now, the company's paid in total for all these lines of business 7.9, well, it's in dollars actually, it's supposed to be in thousands, but doesn't matter, 7.9 million, 8.09 million, 9.3 million. Now we're forecasting 11.250 million for the next calendar year, which seems a little bit high. And the reason it's high is because the trends going forward are a little bit higher than the past. In other words, we used a conservative scenario. And the reason we use a conservative scenario is because we wanted to match our mean reserves by that held by the company. Remember, these are simulated triangles based on the real data, based on the real data, the model that we fitted to the real data. So, usually one would expect 7.9, 8.09, that's an increase of about $1 billion. No, sorry, it's a very small increase. That's an increase of about 400,000. So you'd expect maybe this to go to about 9.799, but not 11.25. Okay, let's look at the reserving table. That's the F. And you can see that 58 million is the total fitted values across all the triangles. 58, just under 58.2 is fitted. 58. We get a very good fit to the aggregate because it's always easier to forecast the sum of many numbers than the sum of fewer numbers. But if you look at REA, it's pretty volatile. You'll see that very often the fitted values, the means of the log normals, are pretty far away from the observed, and if the observed is large, it's very large. But REA, the residuals do have a normal distribution, and if you look at the model display, click on model display, you'll see that if you look at standard deviation, the standard deviation of the reserved of the normal distributions is 0.6. That's very high. It kind of means the corresponding coefficient of the log normal on a dollar scale, just based on process variability, will exceed 60%. So if we go back to the forecast table, just click on F, and we're still on the REA tab, you'll see that 20 on 27, the CV is very large, well in excess of 60%, but it also includes parameter uncertainty here. Let's go to the forecast summary, and let's go to the aggregate tab. And we've got the aggregate tab. Okay, we've got aggregate. We're on the aggregate tab. That's the accident years. Let's look at LOB. Let's look at LOB comparisons. So the largest line lie right is REB in terms of reserves. REA is 16%, but you'll notice that the coefficient of variation, CV of REA, is pretty large. It's 39%. And also notice that the CV of the aggregate is lower than the CV of most lines of business. If we go back to the forecast table, F, with the system you are forecasting all these log normal distributions. We have, going to the forecast summary, back to the forecast summary, and now to aggregate summary by, just click on accident years, not summary by data sets. Just click on accident years, and we can see the aggregate mean is around 24.7 million, standard deviation of 82 million. If you look at calendar years, that's the calendar year liability stream. It's the calendar year liability stream, very important for calculating the cost of capital. That's for the aggregate, and then of course then you can see it for every line of business. Now it's interesting, if you look at HOFO, it decays immediately. Why? If you look at the model display for HOFO, you can see that you pay most of your money in the next year, and thereafter you pay very little money, and the calendar year trend is zero. the liability stream by calendar year depends on 2 or 3 features of your data. The 2 most important features is the development year pattern, and then the other one is the calendar year trend, assuming going forward, the assumption going forward. If the development pattern peaks in development year 7, say, then you pay a lot of money for the next 7 years, everything else being the same. The higher the inflation going forward, everything else being the same, the more money you'll pay later. If you go back to forecast summary and you look at something like workers' comp, it's 157, it doesn't decay that quickly. If you look at something like OLOC, double C, it actually increases 395, 420,000. So let's now look at the model display for OLOC, and you can see you're still paying a lot of money for the next 2 years, okay? And then it starts decaying, at first not very fast, and only by development year 4. So let's look at the forecast summary. So if you go back to forecast summary, you can see 395, 420, it doesn't decay that fast, okay? So those are the 2 features, I guess the process variables, which actually determine the liability by calendar year. And of course, when you discount it, that liability will have a, the liability stream by calendar year is going to be very important when you do your discounting. Now let's go to forecast with the downward arrow. Choose the combined forecast table. It includes the next underwriting year. That's for this particular line. We can look at the aggregate. We also have the forecast table just for the future accident periods, okay, by aggregate and every line of business, which is important for pricing. And we also have 3 forecast summaries. So you can go to the forecast summary. Let's look at the combined forecast summary. And it also has risk capital allocation. This is by accident years. Well, that's for a particular line of business. Let's look at the aggregate tab. And in the aggregate tab, you also have LOB comparisons. That's for the combined. You've got summary by data sets, risk capital allocation. You've got risk capital allocation by accident years and calendar years. In fact, this is both for the reserves, future underwriting year, and the combined. You get all these tables. Let's go back to summary by data sets. You also get correlations. Okay, so you get a lot of information. So there are 3 forecast summaries. There are 3 forecast tables. A lot of that information can be included in your report template, which we'll do in a subsequent study, and also you can also use com script to extract any of this information and create new tables. Okay, thank you.